Oh.
Oh no, I can't sit down. I bruised my tailbone.
Okay. What questions do we have? So today I assume most of the questions are going to be on homework 5. Since we have a quiz on homework 5 in just a few hours. So, what questions from homework 5 do we want to look at? 9, 6, 5, 1, 7, 3,
8G.
8. Part G. What else do we got?
11.
11. Okay, that seems like a good start. Okay, let's see how fast we can go through these. Someone go ahead and read problem 1 to me.
When solving most weak basis dissociation equilibrium problems, two major assumptions are typically made. Explain when you can make each assumption and what allows you to do in the problem, and what it allows you to do in the problem. How can you check that made a good assumption? And A is the contribution of OH from the base is larger in comparison to the contribution from the auto-ionization of water.
And part B?
B is the amount of base that dissociates water is small in comparison to the initial base concentration.
So I'm going to call these 2 different things. Then maybe we'll be like, oh. And again, this is a fantastic question. You saw in the first midterm, I asked this question. I'm going to ask this question on the second midterm. I'm going to ask this question on the final. Right? This whole idea of when can we make approximations and are the approximations good or not is one of the most important things that you're going to do throughout the rest of your careers, regardless of what your major is. You're going to be neglecting some things and focusing on other things, and you have to be able to justify that to somebody at some point. So this OH is large compared to water is another way of saying water is negligible. In its OH minus contribution, right? This is the, we can ignore water, right? When we write down our ice tables, when we write like B goes to BH plus OH minus, we say, oh, it's okay to start with a 0 on the OH minus because the amount that water is going to auto-ionize is small. And that is generally true as long as the amount disassociating, as long as we're not dealing with something that's a really, really low concentration or a really, really weak acid, right? Generally, that's going to be okay. The only place where that's not okay is like pH 6.9 to 7.1. It's a smaller range than you would think because any acid or base you put into water will actually affect water's equilibrium as well. There's this secondary effect. So that's how we think about this one. This one, I'll put in different terms. Second part is really just saying X is small, right? And the language in it is a little bit wrong technically because a base doesn't disassociate, a base becomes associated, right? If there's a difference in direction, and it's probably my fault from cutting and pasting. But when we're dealing with an acid, we have a proton being donated. When we're dealing with a base, we're having a proton be accepted. So it's really an association, not a disassociation, but it's still the X is small approximation, the idea that the initial concentration here is going to be large compared to this, and we can always look at it. You can always consider the Kb versus the initial concentration of the base, right? And that's going to be allow us to do this kind of first assessment of as long as the Kb is much smaller than the initial concentration of the base, this is probably going to be a good approximation. Same thing we did with our acids, right? As long as Ka was much smaller than our initial acid concentration, X is small work. Really, we should check it after we use the approximation. What x value do we get? And is that x value smaller than the initial concentration or not? And we usually go, in this class, we do a 10% error is okay. Other classes, 5% error is what they aim for. Some classes, 1% or less. So depending on how accurate we want to be, there's going to be a different amount of whether that approximation is okay or not. Same thing in the rest of our lives. There's going to be how okay is it to neglect this thing, this person, that person. How much neglect can something handle based on how much we care about it, how much detail do we want to have, how much understanding do we want to have. So that's problem one. Is that satisfactory?
C.
Oh, what's part C?
Do you make either of the above assumptions when solving most strong base problems? If so, when does this assumption fail?
Do we assume x is small with a strong base? What's the KB for a strong base?
Really small.
Really big.
Really
Oh,
big, right? Because that's going to tell us, what do we assume a strong base does? 100% disassociation. 100% disassociation would mean a KB much, much larger than 1. Which means a strong base is exactly where x is small fails, right? We can never actually use the x is small approximation when we're looking at a strong base. What about water being negligible? Is that generally true? Yeah. Did I spell negligible right? I feel like I need a couple more L's and I's in there.
That's it.
Okay, great. So water is usually negligible. Right now, I tossed in an extra word. We all shook our heads yes. When is it not okay? When are we going to have to worry about the contribution of water?
Here, pH 7.
pH 7, right? When we get close to the pH of water, where water is going to be contributing a lot. Now, if we're adding a strong base, are we going to be at pH 7? No. What would make it so adding a strong base would put us close to pH 7?
Strong acid in solution.
Strong acid solution, we could do a reaction, and if we reacted to the point where they were neutralized, we'd be there. What else? We did a problem like this 3 weeks ago for a strong acid. What does a strong base put into water? Well, you know, I was thinking Irini's definition. Strong bases are almost always those hydroxide donating compounds, the 100% disassociation, right? Bronsted-Lowry definition kind of changes that idea, but still we can think about it in terms of hydroxide. So we say, okay, it's going to put hydroxide into solution. How much hydroxide, if I had 0.1 molar sodium hydroxide, how much hydroxide would be put into solution? 0.1 moles per liter. At what point, with that in mind, what about if it was 0.01? 0.01 moles per liter. At what point would water become significant again? Significant again. What's that?
When it matches the concentration
Of
the hydroxide.
yeah. So what kind of base would that be? You all did this on homework 4 with acids, right? What was the answer to this one for acids? Okay, let's think about this. So we did this problem in class. It was when we were first learning about the autoionization of water and this approximation. And we did a very particular calculation with an acid. And it was a strong acid, but there's something special about that strong acid. Let's think about this. How much base is water going to put into solution? Wait. So water is going to split itself up. The kW for water is
1 times 10 to the negative 14.
yes, we got that one. Okay, 1 times 10 to the minus 14. So if we looked at the autoionization of water, we're gonna have 2H2O goes to H3O plus OH minus, and that's going to give us Kw equals 1 times 10 to the minus 14, and it's also going to be equal to my OH minus concentration times my H3O plus concentration. Without doing the calculation, what's the pH of perfect neutral water? 7. What's the concentration of OH minus in perfect neutral water? If we know the pH, what's the pOH of perfect neutral water? 7. What's the concentration of OH minus in perfect neutral water?
10 to the negative 7.
Yes! Our OH minus concentration, and we can see that just here, right? This is going to be like x squared, take the square root, that gives us 1 times 10 to the minus 7 for both. Is 1 times 10 to the minus 7. Molarity, right? So when we look at this, we say, okay, at what point would this be significant compared to a strong base?
When it's at least 10% of it. Or, sorry.
Yeah.
Like, comparative.
Yeah.
Basically.
Right. So the phrase I was looking for, and then I'm hoping you all go, oh, so do that even if it's not true. If we were using a very dilute base, right? Thank you for humoring me. Right. So the problem is, if you had like an entire liter of water and you put 1 drop of base in, right, that base is going to be very dilute. The amount of OH minus you're adding from that 1 drop of base is going to be small compared to the amount of OH minus added from water. And we did that calculation for dilute acids, where then we added 1 drop of acid, but we got a pH above 7. And we were like, oh, that's not possible because we added acid. It turned out we neglected water. If you put in 1 drop of a dilute base into water, you'll get a pH below 7, and you'll be like, that doesn't make sense. We added base. We got to take into account the contribution from water in those extremely dilute cases. I'm glad you reminded me when we went over that. I thought you'd all be like, oh yeah, no problem, dilute cases, right? Anytime our concentration of our weak acid or weak base is on the order of the concentration of hydroxide or hydronium from water, that is to say, anytime the strong base concentration is on the order of 10 to the minus 7, we're going to have to worry about how water contributes. Okay? But since the Kb is still large, we can still, the X is small is going to fail, right? The large Kb is going to say that it's still going to completely disassociate. So X is small always fails. Water is negligible, fails if we have dilute bases. Great. Any questions on that? Giving me ideas for quiz questions and midterm questions. Remember, those concept ideas are the things that I like the most. I think the math is too easy. But the concepts, the ideas, that's the important thing. So that was problem 1. What do we got for problem 3?
Yeah, I'll read it. A 10 milliliter solution of 0.1 molar methylene solution. I don't know. Is titrated
You said it right.
Good.
That's all we need.
With 0.1 molar nitric acid. Calculate the pH after each of the following additions of the nitric acid solution. So it's initial pH first. Yeah. 2 milliliters, 5 milliliters, 7, 10, 12, and 14.
It's going to take me a while to go through all of these. So let's do some problem analysis. Let's do some problem breakdown and think about where we can do things easier and where it's going to be harder. I can pretty quickly do a molarity of weak base, volume of weak base is equal to molarity of strong acid, volume of strong acid. Plug in 0.1, 10 equals 0.1 V, and get V to the equivalence point is equal to 10 milliliters, right? So I can instantly recognize where the equivalence point is, where the midpoint is. That also allows me to recognize all of my buffers, and of course I've also got my initial, and then I've got my excess acid. Right? So the first thing I do when I'm thinking about this problem is I just break it up into the different calculational parts, right? Because we've learned about these titration curves, but we've really learned about it in chunks. We did the initial point and the equivalence point first, right? We learned those calculations. And for the last week or so, we've been doing these buffer range calculations. We haven't really done much in the excess acid area because I find it kind of boring. But we can do one of those. This allows us to kind of think about each problem. How many people need me to do an initial pH calculation? 1 through 5s.
5 being...
5 being, no, move on. Okay. That's most people moving on. How many people need me to do a buffer range midpoint calculation? 1 through 5. 5 being like, no, let's move on. Okay. Buffer range calculations. Set of 1 and 1. Okay, let's see. So it's a couple lower numbers. Let's do some buffer range calculations here. And we'll definitely do an excess acid one, and you'll see why I never bother. It's just however much. It's just the concentration of your excess acid is your pH. Boring. Same thing with the weak acid strong base. Excess concentration of your OH is your POH. That's it. That's all there is. So let's go ahead and look at this. Now, we could do it the... option 1 is do it the long way. Option 2 is do it the shortcut. It's mostly shortcut, a couple long ways. I'm going to go through the long... I'm going to set up the long way, but then we'll just let that lead into the shortcut. So I'm going to do my reaction is going to be, I'm just going to call methylamine B. So I'm going to have my base. I'm just going to say my nitric acid is just H3O+. That's the only important thing from it. The nitrate does nothing. I mean, not nothing. It's a counter ion. It balances charge, all of that. It's a strong acid because it's an oxo acid. There's all kinds of great things we could say about nitric acid. But in terms of the reaction here, all that matters is we've got the H3O+ in solution to react. I'm going to actually calculate my moles here. This is going to be 1 millimole. I'm going to do it generically so we can do all 3 points. I'm just going to call it 0.1 V and 0. I'm going to subtract 0.1 V, subtract 0.1 V, and add 0.1 V. Now, I know that if I'm in my buffer region, my acid is the limiting reactant. It's only past the equivalence point that the acid is excess. So that should be okay. I'm going to have 1 minus 0.1 V. I'm going to have 0. And I'm going to have 0 plus 0.1 V. Right, that's my stoich, my stress table. Now I'm going to go ahead and set up my ice table. And for my ice table, I'm going to be looking at, since I've got conjugate acid and weak base, I get to pick which one I look at the equilibrium of. Because I've got both present. So both equilibria are happening. I get to choose. Now, the question is asking us to calculate pH. So it's going to be easier to do the equilibrium of the... Yeah, the weak acid, the Ka. So I'm going to look at this in terms of BH plus H2O goes to B plus H3O plus. Right, and this is going to set up my ice table. I'm going to have 1 minus 0.1. Whoops, lies. I flipped the table and I almost forgot to flip my values. Be careful when you're doing this. Don't do like I just did. I'm going to have 0, and I know it's silly to leave a 0 plus, but remember we ran into that problem in the past. 0 plus 0.1v, 1 minus 0.1v, and 0 minus x plus x, approximately 0 plus 0.1v, approximately 1 minus 0.1v, oops, and x. Now, I'm going to set this up since this is set up as a Ka. I'm going to have Ka is equal to concentration of B over BH, products over reactants, times concentration of H3O+. This will lead us to our shortcut, right? We get pH is equal to pKa plus log, give myself a little more space, log of products 1 minus 0.1v divided by reactants 0 plus 0.1v. Now for those 3 points, 2, 5, and 7, I can just plug in whatever I have for v and solve, as long as I've got the Ka. Now for this problem, I assume you had to look up the Ka for methylamine?
Yes.
Or the Kb rather. What's the Kb equal to?
4.4 times 10 to the negative 4.
We can use that to calculate the Ka. What's the Ka equal to?
2.27 times 10 to the negative 11.
So then I can plug in my pKa, I can plug in my volume for all 3 of these points, and I can solve. Right? I've set this up. We're doing problem 3 on homework 5. Right? So this allows us to do all 3 of these points. I don't need to set up a stoichiometry table and an ice table for each of these 3 points. I can use this equation for all 3. Right, and you can notice what's going to happen at the midpoint. What should be the pH at the midpoint? pKa. Notice, even without memorizing that, the stoichiometry and the equilibrium bores that out, because if I had 5 milliliters divided by 5 milliliters, I'd have my 1 minus 0.5, which is 0.5, divided by 0.1 times 5, which is just 0.5. Log of 0.5 divided by 0.5, well, 0.5 divided by 0.5 is 1. Log of 1 is 0. I just get pH equals pKa. Right? We didn't memorize that as like a magical thing. It comes out of the stoichiometry and the equilibrium. We did that calculation 4 times before I told you pH equals pKa. And still, some people are like, I don't know, I just thought it was true. It's like, no, we did the calculations. So, we should be able to do all of these. Did anyone do these?
Yeah.
So, what's the pKa?
pKa is 10.64.
Right, this is going to give me some information. I know at 2 milliliters, my pH has to be higher than 10.64, and at 7, my pH has to be lower than 10.64 because I'm adding acid. What is it at 2 milliliters? We plug in 0.8 divided by 0.2, take the log of that.
11.24.
And then we're going to have 0.3 divided by 0.7, take the log of that, add it to the pKa. 10.3? Right? If we can skip all of this setup and just be like, oh, this equation works. I understand how it works. I understand all the parts of it. I understand the stoichiometry in it. We can do those 3 problems like bam, bam, bam. Super quick. Right? Because all we're looking at is the ratio of conjugate or weak base to conjugate acid. That's all we're looking at is the ratio of weak base to conjugate acid. Good? Okay. Are we ready to move on to, yeah?
Can you use that equation even if you're not in the buffer region?
No. Right? This equation only works in the buffer region for 2 reasons. I'm trying to think if there's a third. For at least 2 reasons, right? We used the exasmall approximation for the BH plus, and we used the exasmall approximation for the B minus. Just the weak base. If we are outside of the buffer range on the acidic side, this exasmall approximation fails. If we're outside of the buffer range on the basic side, this exasmall approximation fails. So if we try to use this equation when we're outside the buffer range, our approximations become bad and it doesn't work as well as we want. It might, depending on how far out of the buffer range we are, we might have like a slight error to an enormous error, right? Because the pH plus or minus 1, the pKa plus or minus 1, gives us some safety. We could probably go to pKa plus or minus 1.2, 1.3, and get even further outside of there, but the approximations start to get worse and worse very fast on a logarithmic scale. So they go from being good to being really bad very fast. So can't use it outside the buffer range because of that approximation. Equivalence point. Ready? Okay. Can't use that approximation. Let's just go ahead and erase it. I'm also going to erase the equilibrium because something might change with that. But for the stoichiometry, everything stays the same except for now I can plug in that my volume is 10. And you'll see another reason why. So this goes to 0, that goes to 0, this goes to 1 millimole. Notice, I've converted all of my weak base into conjugate acid. That's the definition of the equivalence point, right? I have an equal amount of base and strong acid that converts all of my weak base into conjugate acid. Again, careful with your vocabulary. We've got a weak base, we've got a strong acid, we've got a conjugate acid. We have to be careful with our vocabulary to make sure we're not confusing which thing we're talking about. Now, when I go to set up my equilibrium, I don't know what color I want. I wish I had a purple pen right now. In any case, when I go to set up my equilibrium, notice I now don't have a choice, right? I can't put weak base in water and say, how does that react with water? Because I have no weak base left. I only have my conjugate acid, so I have to do BH plus goes to B plus H3O plus. Set up my ice table. I'm going to have 1 divided by 20. I'm going to have 0. I'm going to have 0. Notice, again, I actually have to turn this into a concentration because I'm not taking a ratio anymore, so I don't get to do the cool canceling total volume trick. So I actually need to convert this into a concentration. Why did I do 20? 10 mils added, 10 mils at the start. Total volume is 20. What is 1/20th? 0.05?
Yeah.
I take that millimole, I divide by the total volume, I get 0.05 molarity. I go minus x plus x plus x. I say approximately 0.05 x, x. I said KB is equal to x squared divided by 0.05. Oh my god, it's just like we're doing an initial pH calculation all of a sudden. At the equivalence point, after you take, oh, sorry, what mistake did I make? Ka, I got carried away with my weak acid thinking. This is Ka, I've got H3O plus, I've got a weak acid, that's Ka. So, whenever we're at the equivalence point, it's the same as doing an initial concentration of acid or initial concentration of weak acid or weak base after we get the diluted value. After we get dilution into account, it's the same calculation as the initial. It's the same, it's all the same stuff still. So we can solve for this. The nice thing about doing the weak base, the conjugate acid, is in this case when we solve, our H3O plus is equal to our x. Plug in our Ka, 2.27 times 10 to the minus 11 times 0.05, then take the square root. I don't think I can do that in my head. 12. 1 times 10 to the minus 12. 1 times 10 to the minus 6?
Yeah, 1.6 times 10 to the minus 6.
Take the negative log, get a pH of about 6, 5.9. Ta-da! It really is, at the equivalence point, we're just doing something that's like an initial. If we're doing a weak acid titration, the equivalence point is a weak base initial pH-like calculation. And if we're doing a weak base, the equivalence point is a weak acid initial calculation. They're the same things we've been doing. Shall we go ahead and do point G, just to see how boring it is? Okay. Everyone okay? Questions? Okay. So, if we go to point G, again, we're going to get rid of that equilibrium. We're going to now change our volumes. Again, we're going to go to, I said let's just jump to 14 because it's the same. Oh, I already made a mistake. What mistake did I make?
Subtracting the 1, not the...
Right, so if I do 1 minus 1.4, I get a negative answer here. The weak base is no longer excess. The strong acid is now excess. So I actually have to change my stoichiometry around a bit. I'm still starting with 1 millimole here. But now I've got 1.4 millimoles there. I got 0 there. My weak base becomes the limiting reactant. I'm going to have -1, -1, +1. I'm going to get 0, 0.4, and 1. Right? This is because we are now looking at the situation where the acid is in excess. Do we need to do an ice table? Not actually, but let's set one up to see why not actually. Right? So notice I've only got BH plus present, or I've got BH and H3O plus, so I'm going to set this up as BH plus H2O goes to B plus H3O plus. I'm going to set this up. This is 1. This is 0. This is 0.4. That starting amount there, and we can also do divided by 24. Divided by 24, right, that total volume. The fact that I have H3O plus in my initial, when I do my change, -x plus x plus x, to get to my equilibrium, this is approximately 1/24. This is x. What's my H3O plus concentration? Did I need to do my ice table to figure out this concentration? No, I already had it. It was just the excess amount. So actually, I didn't need to do this at all. All I had to do was the negative log of 0.4 divided by 24 equals pH. All I had to do was get the dilute concentration of H3O plus in excess, take the negative log. That's all. How much extra do I have? What pH does that lead to? Once we go past the equivalence point, the titrant, the thing we're adding, always dominates. And it's just how much titrant you add and what's the concentration of the titrant in your beaker. That's all that determines the pH at that point. That's also part of why all titrations look to end the same way, because at that point you're just adding more and more dilute acid. And you're just seeing the pH just slowly creep up as that concentration slowly creeps up. That's it. Good? Okay. I think this will also answer a lot of problems in 6, 9, and part of 8. Because it turns out that 6, 9, and I think it might be 8, maybe it's 11, but there's several titration problems like this, and they are all the same thing. I mean, if you want, I can go through a bunch more titration problems. That's what we're doing in class today, too. That's what we've been doing for weeks. But I'll do it still. I'll do it still. Any questions before I erase this? Okay. Notice, one last thing I'll say. Notice at its root, everything we did, stoichiometry and equilibrium. At its root, whether we hate this shortcut or love this shortcut, whether we understand all these points or don't understand all these points, stoichiometry and equilibrium is at the core of everything we've done. Okay. That was problem 3. What is problem 5? We can hand the homework around so someone else can read it. No one else has it.
Consider a buffer made from 1 mole of NH3 and 1 mole of NH4 plus and 1 liter of water. A is calculate the pH of the buffer. B is write out the neutralization reaction when HCl is added. C is write out the neutralization reaction when NaOH is added. There's 2 titration problems.
pH when we add
pH of buffer after 0.1 mole of HCl is added, and then E is the same thing but with 0.5 moles.
Is that it?
There's one more. It says how many moles of HCl do you need to add to lower the pH by 1 pH unit?
I'm going to call it pH initial minus 1. Does this problem look familiar? Homework 4 was on the quiz as well. Right? This is that exact same problem. It's the exact same logic. It's the exact same everything. Except for because we've changed what the system is, we're changing our Ka. Right? That's the only difference. Which means, and that's a significant difference in terms of the functionality of this buffer, but it's insignificant in terms of the calculations of this buffer. Right? Changing the conjugate pair has a huge impact on the function of the buffer, where the buffer is useful, but it doesn't really change the calculations. To calculate the pH, we're going to be using pH equals pKa plus log. Let's see, we'll do moles of conjugate base divided by moles weak acid. And then we have to be careful. Plus, let's see, I'll do moles of HCl first. Right, plus the moles of HCl we add. If we're adding acid, we increase the amount of weak acid and we subtract the moles of conjugate base. Now, for the initial pH, do we add any acid or any base? So those parts are zeros. The moles of conjugate base is 1. The moles of weak acid is 1. Log of 1 is 0. So for this first one, pH is just equal to pKa. The pKa for this thing is 10 something?
9.25.
9.25. Great. The reaction with HCl, again, the thing that becomes important is that we're going to have NH3. The important thing in the HCl is just the H3O+. The NH3 is going to be a proton acceptor. That's going to go to NH4+ plus H2O. When we add base, sodium hydroxide, the hydroxide is the important thing. Is hydroxide going to react with the NH3 or the NH4? NH4. So we're going to put NH4 there plus OH minus goes to NH3 plus H2O. These two neutralization reactions, whether we're adding acid or adding base, is what changes the stoichiometry inside of this equation. Whether we're doing pluses or minuses on top, and whether it's HCl or NaOH, that's going to be because of these two neutralization reactions. Now we can go ahead and do part D. Part D, again, this was on the quiz. Part D is pH. I'm just going to plug numbers in. It's 9.25 plus log. Moles we start with is 1. Moles that's added is 0.1 divided by moles we start with 1 minus plus moles we added 0.1. Yeah.
Just for clarification, since it's in 1 liter, then we can just do the moles without like calculating.
Yeah. Well, also because it's a ratio of concentrations in the same total volume, we can always switch to moles. That was one of our important shortcuts. Right, so we're going to have the log of 0.9 divided by the 1.1. We get some value associated with that. Does 9.16 make sense? Conceptually? We add acid, pH goes down. We didn't add that much acid, the pH didn't go down that much. Totally makes sense. We can do the same thing here. pH equals 9.25 plus log 1 minus 0.5 divided by 1 plus 0.5. This does not get us to the midpoint because notice we've got the plus minus. We started at the midpoint. This is going to push us more acidic. We should see our pH go down. We're going to have log of 0.5 divided by 1.5. Is that the final answer? We add more acid, the pH goes down more. Yeah.
So if we were to add a strong base instead, we would flip our signs, right?
Yes, yes. If we were adding a strong base, I'm kind of disappointed that I didn't do a strong base on this one. And I would push the pH the other direction. I did that on homework 4. I got to add that to this homework. It's disappointing. The last one is probably the one that gives people the most trouble, right? We're changing. Notice we're working off this equation blue every time, but we're changing what our unknown is. And in all of these, we've been using the same unknown, which is pH. This one, we know the pH, and now we're doing a different unknown. So if I want to go to a pH that's 1 less than this, I'm going to be going to a pH of 8.25. I'm going to have 8.25 equal to 9.25 plus log of 1 minus x divided by 1 plus x. Solve for x. If I do 8.25 minus 9.25 to the power of 10, I'm going to get 0.1 is equal to 1 minus x divided by 1 plus x. And then I just got an algebra, which is why I made a scared noise. Algebra. I'm going to have 0.1 plus 0.1x is equal to 1 minus x. I'm going to add that over, subtract that over. I'm going to have 1.1x is equal to 0.9. I'm going to have x is equal to 0.9 divided by 1.1.
Yeah.
What number do I get when I do that?
0.82,
Does 0.818 moles of strong acid make sense? Let's do a little thinking real quick and get some conceptual idea. We know that it needs to be more than 0.5 because we did the calculation for 0.5 and that wasn't far enough. We know it has to be less than 1 because 1 would push us outside the buffer region and would not work at all. So we know it has to be between 0.5 and 1. Here's a number between 0.5 and 1. Great. If we got something less than 0.5, we did something wrong. If we got something greater than 1, we did something wrong. Notice, all of our weak base problems on this homework, they're really the same. Like, when I made homework 5, I literally cut and pasted homework 4 and just changed all the acids to bases. I even left the numbers the same. I just changed the acids to bases. And for some reason, it freaks people out, but it's all the same stuff still. That was problem 5?
Yeah.
Problem 5. Okay. We ready to move on?
Wait, I had a question.
Yeah.
So when you were saying earlier, if you were adding strong base instead, you flip the signs.
Uh-huh.
You're talking about the signs inside the parentheses.
Yes. Yes, you flip the sign inside of the parenthesis because you're flipping which reaction you're doing. Notice, the reason that adding an acid subtracts from the NH3 and adds to the NH4 is because the NH3 is a reactant. When we subtract from reactants, the NH4 is a product. We add the products. If we switch what the reactant and product is, we also have to switch that sign.
Okay, got it.
Other questions? Great. That brings us to number 6.
That's another titration one.
It's another titration one. I'll let you all do that on your own.
Can we do number 7?
If you're like, wait, I really wanted to see number 6, go watch the video. Go like rewind the video, look at number 3 again. It's the same thing. And we can do it again after we get through these questions. We can go back to it. Number 7.
7 says methyl orange has a pKa of 4.2. Its protonated form, abbreviated HIND, is red, and its deprotonated form, IND minus, is yellow. And it says A. When would this indicator be useful in titration?
What was this pKa?
pKa 4.2.
You know, it just occurred to me that I think because of the way I was hopping around to do weak acids or polyprotic acids, I think I skipped my 2 slides on indicators. So I'll have to do that today. This problem won't be on the quiz. However, indicators are useful next to their midpoint. So anytime, so here's what we want to think about. And every indicator, I'm getting a little ahead now, so if you're watching this, great. Okay, so every indicator we can actually think about in terms of a weak acid, where I can have my red to yellow. And if I drew a titration curve for my indicator, tell me, so where's it going to be red? Is it still going to be red through here? Here it's going to start to switch to orange. I don't have a yellow marker, so I'm just going to switch to black. Here it would start to switch to black. Or, sorry, orange. Yellow. That's yellow. I don't have a yellow marker. It's the best I can do. So when we look at this, we say, okay, so where is this going to give us some distinction in terms of what's going on? What's that next to? It's the buffer region, which is going to be next to midpoint, the pKa. So for any indicator system, it changes colors through its buffer region. Now that means the indicator is good for detecting any pH that is in its buffer region. So this methyl orange is good for detecting any change next to a pH of 4.2. The thing that confuses most people about indicators is because they think indicators are for buffer regions. No. The indicator's buffer region is where it's useful, but it can be used to detect anything in that useful region. So if we had a titration, if we were doing a weak base titration that's equivalence point was like 5.0, this would be useful because that equivalence point is next to a pH of 4.2, plus or minus 1, right? So it would start to change. It would be, if we were doing that, if we were doing a weak base, it'd be yellow, it'd be yellow, it'd be yellow, it'd be yellow, and then as we get to the equivalence point, it would start to turn orange. And that first appearance of orange would be the equivalence point of that titration, right? So an indicator is useful at a target pH close to the buffer's midpoint. The key word there is buffer's midpoint, right? We have to make sure we're thinking about all of our systems, because now if we're doing an indicator and a titration, we've got a weak acid and a weak base in our indicator, then we've got a weak acid and a weak base in our system, and we also have a strong acid or a strong base that we're titrating with. We end up with 6 things that, well, no, that's only five things we have to worry about. So we have to be clear whether we're talking about the midpoint of our weak acid system, the midpoint of our indicator system, the equivalence point of our weak acid system, the equivalence point of our buffer system, or something else, right? We have to just be careful with the vocabulary. So I'll say it again. A buffer is useful, and we're going to do this in class today as well. A buffer is useful when the target pH, whatever pH we're trying to detect, is close to the midpoint of the buffer system. Cool. So that was just a definitional thing. Even though I didn't do that in class, guess what? There's a really nice page-and-a-half about it in the textbook that is very readable. Like, in terms of sections in the textbook, the one on indicators is probably one of the most readable and useful. So if you haven't been keeping up with the textbook, this would be a great place to keep up with the textbook. Number 9.
It asks for other parts too. I don't know if you want to go.
Oh, what are the other parts?
At which pH would 50% of the indicator be protonated?
Midpoint.
Yeah, and then at which pH would 20% of the indicator be in its red state?
Ooh, that's interesting. So we would say pH equals, what's the pKa for this thing we said, 4.2?
Yeah.
Plus log, we want 20% protonated. That means we want 80% unprotonated. Solve. Now, I didn't do much explanation here because y'all did lab, right? And so you talked about protonated versus unprotonated forms of indicator. Now keep in mind, I kind of also want to label this, again, because we start dealing with so many things. I like to put pH IND to make sure I'm talking about the indicator here. I put 0.8 IND, 0.2 IND. This is about the indicator. Because we can do the same calculation for the weak acid, weak base system that we're curious about as well. Right? An indicator by itself is not really that useful. It's always the indicator with another system that we're actually practically interested in. So I encourage extra labels rather than less labels. Was there another question after that?
It says, if you wanted to make a buffer that would keep this indicator around 50% protonated, what materials could you use to make that buffer? Use appendix H and I for possible materials.
So now let's say, okay, we want to make a buffer that keeps this thing 50-50. I just want to find a weak acid that has a pKa of 4.2. Right? Because if I want to make a buffer that keeps this thing perfectly orange, 50-50 mix, I need a buffer whose midpoint is close to the midpoint of the indicator. So in that case, I want the midpoint of my buffer to be close to the midpoint of my indicator. But but we need those specific terms. And the only reason we're doing it midpoint is because that's what the question asked us to do. It's also kind of useful to have an indicator for a buffer like that, because then as soon as your solution changes colors, you know you broke your buffer. You broke your buffer. You're outside the buffer range. So it is actually really useful to have an indicator that is like over the buffer range will change colors. Because then even one drop of indicator into a giant thing of buffer, that indicator will stay the same color, and you don't put in enough to really affect anything else. Like you put a really low concentration, so it's an insignificant amount of reactants. And then as soon as you get out one side or the other, you can tell. That's part of, if anyone's ever had a hot tub or a pool and you get those funny little like test kits to see how your pool's doing in terms of its health. Anyone? Right? Those are pH tests, and they essentially are checking where you are. They have some other chemical tests they do as well. They have like a chlorination test, a pH test, and a something else test. But they're all indicator systems. Problem 9. Another titration.
It's polyprotic.
It's the same. We can still do it. Do we want to do the polyprotic 1 through 5?
I had a question on H, like specifically, which is the last one.
5 would be moving on, not doing it. 1 would be gotta do it. Okay, people want to do it. So let's go ahead and get this. This is problem 9. Oh shoot, I forgot 8G. Sorry, before I forget.
Wait, 8 is the polyprotic.
Oh, yeah.
Yeah.
Oh, 8 is the polyprotic. What was 9 then?
I think he's asking for a 200 milliliter sample of 0.35 molarity of oxalic acid titrated by 0.4 molarity strong base, and just says to calculate like pH at the first midpoint.
Oh, so it's another polyprotic. They're both polyprotic titrations. Let's just pick one. What do we want to do more, 8 or 9? I'm not going to do 2 polyprotic titrations. They're so important. Well, I mean, we could do it the fast way, but I'm going to do a little bit of extra explanation. 8 or 9? Do we have preferences? No? Should we just do 8 then?
Sure.
Let's just do 8. Okay, we'll skip 9. Kind of the same stuff. Someone read problem 8 to me.
You titrate a 50 milliliter sample of 0.1 molarity malonic acid with a 0.14 molarity sodium hydroxide. Calculate the pH and plot a titration curve for the following volume additions. There's like a lot of them.
Read them out.
Okay, 0 milliliters of HCl, 8.2, 11.35, 17.85, 22.7, 30.4, 35.71, 45.44, 53.56, 59.99, 71.42, and 85.
Great.
And then there's another conceptual one at the bottom. But
We'll get to that.
Yeah.
We'll get to that. Whew. Yikes. Y'all picked a problem. Okay, let's go ahead and do our conceptualization thinking first. Oh, does anyone have the KAs for this thing?
I got 1.4 times 10 to the negative 3. That's what I got.
And?
For K82, I got 2.04 times 10 to the negative 6.
Ooh, 3 orders of magnitude difference. Starting to get that Ka1 much bigger than Ka2 is not as good as I want it to be, but it should still be okay. Let's do some thinking first. Molarity of weak acid times volume of weak acid equals molarity of strong base times volume of strong base. We've got 50 times 0.1 is equal to 0.14 V. This gives me the volume to the equivalence point is 43. Am I even close?
The first equivalence?
Yeah.
I got 35.7 71.
Cool. So, what's half of 35.71?
17.85.
So we can start looking at some things. Midpoint 1, equivalence point 1, buffer 1, 35 plus 17 is going to be 52? 50, is it 50, what's 35.7 plus 17.85?
It's 53.56.
That is midpoint 2. And then 35 times 2, 35.7 times 2.
I think it's the 71.
There's buffer 2. Okay. So, let's do the easy ones first. I didn't really give myself enough space, but that's okay. pH at midpoint 1, 2.9.
I got 2.85.
pH at midpoint 2,
5.7.
pH at equivalence point 1, 2.85 plus 5.7 divided by 2.
I don't know where it is.
Should be something like 4.3.
4.27.
So notice, you can kind of see like these three numbers, they're closer than I'm actually really comfortable with. So in terms of a titration curve, this thing, instead of being like a nice, like, ooh, there's one point, there's the other, we're going to get something that's more like it kind of smears together a little bit. Less than ideal, but probably still workable in this case. Now, all of those points, we used kind of the shortcuts of pH equals pKa1, pH equals pKa2, pH is the average of the two midpoints, right? Everything else we're going to have to be a little bit more careful. Everything in the buffer region 1, we can use pH equals pKa1 plus log, I'm just going to call it 5 millimoles minus 0.14 V divided by, this is an acid, and I'm adding a base, so that would be 0 plus 0.14 V divided by 5 minus 0.14 V. Right? I can now plug in 8.2 for my volume, 11.35. I could even do 17.85 again if I wanted to. 22.7 and 30.4. All 1, 2, 3, 4, 5 of these problems can be done with that equation. Right? All of that. You don't need me to do another initial pH calculation. We've been doing that for 4 weeks. Ka equals x squared divided by initial divided by 0.1 solve. So that lets us do all of that. Then we can skip down to these 3 problems. We've only got 2 more to do. And we can do it as pH equals pKa2 plus log. There's something special that I didn't mention yesterday in class because we ran out of time, but I figured you'd all get it by doing the stoichiometry. Did you all get it by doing the stoichiometry? Here's what happens. We still have 0 here. So essentially what we have to realize is that at this point, all of our H2A has been converted into HA minus. So when I start doing my second titration, because this thing looks like this, I can essentially say, look, I'm doing a whole new titration here, right? So after I get past the first equivalence point, I'm essentially just doing a new titration. I can do everything for the new titration as if I'm just doing the second proton. Assuming my separation of Ka1 and Ka2 is good enough. In this case, we're going to say, might not be good enough, but we're going to pretend like it's good enough. So at this point, I should have 0 of my A2 minus. I should have all of my HA. And then I'm going to just do the same thing, plus 0.14. I'm going to do something funny here, 0.14V. I'm going to do minus 0.14V. Why did I leave that extra space next to the volume? This is the part that I thought you'd figure out from the stoichiometry. If I'm ignoring this entire first part, do I want to count that first part in my volume? No, right? If I'm saying once I get to the equivalence point, it's like doing a whole new titration, I need to neglect, for the 45.4, I need to neglect this first 35.71 because that all reacted already. So I have to subtract 35.71 from that volume. Right? I have to subtract the first equivalence point off. To make it so I'm only considering the addition past the first equivalence point to continue the reaction. I'll put a little note. And the reason we do that is because all that stuff's at the first equivalence point already reacted. And it's not there anymore. Now, doing 45.4, 53.5, and 59.9, all the same stuff again. Right? Polyprotic problems are actually no harder than anything else we've been doing. And in fact, they're not even much. The only thing that makes them longer is that there's more points associated with them. But the calculations at this point should be pretty quick. As long as we've got the conceptual thinking behind it to make these kind of shortcuts, right? Again, notice, math, concepts. That's the part that makes this easy, is understanding the concepts. That means 71.4 is the equivalence point, and 85 is past the equivalence point. Which was part G?
Oh, it was the equivalence point. I was just...
Second equivalence point?
Yeah. Or the first one. I just...
Oh, first equivalence point. Oh, yeah, if you forgot about this approximation, I don't remember, somebody came by my office yesterday, and I showed them the derivation of pKa1 plus pKa2 divided by 2.
Yeah.
And they got, like, really mad at me. They're like, why does it take so, like, this is so confusing. I was like, that's why we don't do it. It was really, like, I was doing it as fast as I could, and it still took me 15 minutes. And I was going really fast. I made a typo someplace, but it's amazing. Like, it's like magic to me how everything starts canceling. Like, you end up, like, halfway through the problem, it looks like this super complicated mess of, like, there's no way this is going to get any simpler. And then you put things together, and it's like cancels, 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 cancels. And you're like, wow, it's really just pKa plus pKa. It's mind-boggling how it works out. I like it, but I find it mostly confusing to do it. So I didn't want to do it. Equivalence point 2, do I need to do equivalence point 2? Right? And so there's a couple specifications I should make. This average pKa's works for any equivalence point between two midpoints. And we do the equilibrium table for the last equivalence point. Right? In the past, we always had only one equivalence point, so it was always the last. In our polyprotics, the second proton a lot of times is the last equivalence point. But when we go to triprotics or quadroprotics, pentaprotics, we could go up even higher. The last equivalence point is going to be the one where we have to do an ice table.
You do an ice table for equivalence point 2. Is that
Yeah, for the final equivalence point. So the way we would do that if we wanted to do this is we'd look at our stoichiometry. We don't even have to look at the stoichiometry, right? We can just say A2 minus is equal to 5 millimoles, right? Because at the equivalence point, all of the acid we started with is the new thing, right? Divide by, I want the concentration of A2 minus. So I'm going to divide that millimoles by 50 plus 71.42. Then I can just set KB2 is equal to x squared divided by the A2 minus at equivalence point 2. Because remember, the equivalence points are the last equivalence point of the last equivalence point of a titration is essentially like an initial pH calculation for the conjugate. Conceptually, that's really important because if we get that concept, the math is trivial. It all becomes super easy and straightforward if we get those concepts. Yeah.
And so there we get the concentration of our OH.
Yes, that's the important thing too. Other important thing to remember here, X is going to be equal to OH minus in this case because we're looking at a KB. And then you'd have to take the negative log of that and then 14 minus your POH to get pH. But I'm sorry. I know this class is like super interesting. I really enjoy this class, but by the time I get to week 6, I'm just so bored with these calculations. And keep in mind, for me, I usually teach this class twice a year for the last like 4 or 5 years. So like I've done these calculations a lot. So I get really bored with these because they're all the same stuff. I'm amazed that it still takes me 6 weeks to get this board, but it does. I think seeing people figure it out is still exciting for me, so I like to get people to figure it out. But after I get to this point where it's like, I hope we've got it figured out, that's when I'm like. So, and then 85 mils, excess base. You can essentially do, figure out how much excess base you got, negative log of that concentration is your POH. That's an entire, wow, how long did it take us to do that full polyprotic calculation? Keep in mind, we didn't really do every single calculation. We didn't punch everything into the calculator, but.
There's the last question that asks,
Oh yeah, what's the concept?
why would it be a bad idea to use phosphorus acid in a calculation like this?
Oh yeah, why would it be bad to use phosphorus acid? That is H2PO3. In case you didn't remember your naming conventions for weak acids from 127. If you look at the Kas of that acid are very similar.
Okay.
So then our approximation through the middle, you just don't get to make a nice curve like this that all smears together. Theoretically, you can still do all the calculations, but it gets messy in the middle. I forgot what else I was going to say. Did I do any polybasic problems on the homework? Something that can accept multiple H pluses? I should add that. Guess what? Calculations are all the same. Nothing really changes. Just a little bit of the thinking around it. the pHs you expect are going to be different, but the volume calculations are all the same. Okay. Other questions. So let's see. Which problem? That was 8 and 9.
Yeah.
That leaves number 11.
Yeah.
What is number 11? I'm not even erasing the board at this point. I'm tired. That's a lot of calculations.
It says how much benzoic acid in molarity and moles is left in solution when I mix 100 milliliters of 0.3 molarity benzoic acid with 100 milliliters of 0.35 molarity ammonia.
Oh, we can't do that one yet.
Okay.
We can't do that one yet. We're not learning that today and Friday. That is a weak acid, weak base reaction. So if you're like, oh, we're all done, almost, right? So we're finally at the point where we understand KSP and we understand Ka and Kb well enough that we can start looking at these really nuanced competing equilibria. Weak acid with the KSP, not just the qualitative like we did on homework 2, but actually doing calculations associated with how much you increase the solubility or decrease the solubility. And also weak acid, weak base reactions. A lot of the other 129 instructors actually skip this. I don't think it's done in the textbook particularly well, like in any textbook I've seen. But I find understanding weak acid, weak base reaction is probably one of the most beneficial things for understanding some of the key organic chemistry reactions you're going to be learning next year. At least for me, from a physical chemist standpoint, organic chemists have a different opinion. But I find understanding acid-base behavior really makes sense of why some reactions happen and others don't. Yeah.
So I just have a quick question on 10K. It was asking from each pair, find a K reaction and rank the reactions.
Also, past what we're doing. How many more problems were on the homework? So it seems like
It was up to 11.
it's just 11. So just 10 and 11 are stuff we haven't done yet. But I think there's plenty in 1 through 9
Yeah.
for us to do.
It's good.
Okay, I'm going to go ahead and stop the video. I'll be here to answer questions. If any of you who are here missed problem 3 or problem 6 and really want to see it, we can do it again.